I asked you all to imagine what a spaceship launch looked like, that you immediately think of something like this. Most spaceships have been launched this way over the past 60 years. And although launching from the ground is a great idea, the folks that designed our spaceship realized that it could be done a little bit differently to meet our specific mission. As I mentioned at the beginning, launching a spaceship requires a lot of energy if you're going to space. And if you launch from the ground, you need to put in all that energy starting from rest on the launch pad. One issue is that down low in the atmosphere, the air is very thick or dense, and therefore creates the most friction or resistance and drag, which means you need even more energy, not only to get to space, but to overcome the air resistance starting from the ground. Let me try to illustrate this for you. I'm at home right now, like the rest of you, so I'm going to use some simple Lego to make a simple rocket. So here's my spaceship. Now, let's go add some fuel in order to get us up to space. So this gives us the energy we need to accelerate straight upwards. Now that's great, except the fuel tanks we just added make the whole thing just a little bit heavier. So we really need to add a little bit more energy to get the whole thing off the ground. And that makes us even heavier, so maybe just a little bit more. And you get to the point where you get the final answer. Eventually you can see that the size of our rocket with all the fuel is a whole lot bigger than the size of our spaceship. The designers of our ship wanted to try and make launch as safe as possible for the people inside, as well as making it extremely energy efficient. So here's a question for all of you. Is there any invention you can think of which can climb through the thick atmosphere down close to the Earth's surface and then travel up into the thinner air up above the clouds? And do this time and time again in an extremely safe manner? Yeah, pretty sure I can hear everyone shouting out, it's an airplane. That's correct. Don't forget, sometimes the best design ideas really can be the simplest. So rather than launch our spaceship vertically from the ground, we use a concept called air launch. We attach our spaceship to a specially designed aircraft, a mothership. We named ours VMS Eve. Now, if you're going to have a mothership, you better name it after your mother. And Richard Branson's mom is a wonderful woman named Eve. We fly the mothership all the way up to 45,000 feet, which is higher than you've ever flown even in a commercial airline. Up here, the air is nice and thin. That means our launch is very safe and that we need much less fuel in the spaceship to go the rest of the way into space. So that's the way our spaceship design was tailored to meet the challenge. Now, let's look at the challenge of reentry, coming back into the Earth's atmosphere. I'm guessing that there's hardly any of you out there who hasn't jumped into a swimming pool. Some of you might have even dived from high boards or off cliffs into the ocean. If you've done any of those things, you know that the water slows you down pretty quickly. And then if you don't get it right, it can hurt a bit, or even a lot. The trick is to pick the right shape and the right angle as you hit the water. Now that's exactly the same with coming back from space, except in the air, the atmosphere, rather than the water. The spaceship is traveling very fast as it comes back to the Earth. And just like hitting the water, you need to have your spaceship in the right shape and coming in at the right angle to get rid of all that energy in order to have a successful re-entry. The way that our spaceship does this involves a unique and brilliant bit of design thinking. The inspiration was one of these. This is a badminton birdie, or a shuttlecock, and it behaves in a very interesting way. If you have one of these at home, I want you to try this sometime. Throw the birdie up as high as you can, and then watch it very carefully. What you see is that regardless of how many times you try it, birdie will always come down with the cone-shaped nose leading the way. It won't spin, and it won't come down the other way around, like this. The second thing you'll notice is that it comes down much slower than a ball thrown into the air in the same way. The feathers, these parts here, produce aerodynamic drag. They're like air brakes, slowing the fall and keeping the birdie nice and stable. So if it works for a birdie, why not use it on a spaceship? Exactly what our spaceship does. Now, I'm sure some of you are thinking, yes, but how on earth do you make a spaceship into a badminton birdie? Here's a quick video to show you how we do that. You can see here our spaceship Unity in her feathered configuration. With the wings, we call them feather booms, swiveled upwards to about 60 degrees compared to the rest of the vehicle. Once we get into space, the pilots raise the feather to put Unity into this configuration before re-entry. I've got a model of it here to show you the feather sticking straight up. As the spaceship returns to Earth and meets the atmosphere, this shape will ensure that it automatically turns the right way up and will remain in that position with re-entry slowed very powerfully by the feather, which create a lot of atmospheric drag, just like on a badminton bird. The best part is we don't need any complicated computers or controls to keep a safe re-entry angle. The shape of the spaceship and the laws of nature do it all for us. That makes our system extremely reliable and safe for those inside, something that is very important when we go to space regularly. Once we're back down in the atmosphere, the pilots will lower the feather. And the ship returns looking like an airplane, gliding back to a safe and smooth landing on the runway. All right, we're getting towards the end of our time, and I want to save a few minutes to answer some questions. So if you haven't had a chance yet, please enter your question into the chat window. I hope this space chat has given you a little more insight into the fascinating challenges involved in designing a spaceship. Maybe we've also inspired you a little bit, having heard about how our own spaceship meets those challenges. So maybe you'll have a go at it yourself. Take a crack at designing your own spacecraft with what you can find around the house this week. We'd love to see what you come up with, so again, be sure to share it on social media and use the hashtag #ScienceWithVirginGalactic. By the way, a spaceship not only has to be safe and efficient, but it better look great too, so make sure you include that in your design. Our spaceship is partly silver, like a mirror, and it looks awesome if I do say so myself. The secret is, we actually made it like that to solve yet another design challenge of spaceflight. See if you can figure out why we made the ship silver. I'll give you the answer next week. All right, on to the questions in chat. First question from David: why is a landing skid and not a wheel at the front? It's a great question, David. When the spaceship lands, it doesn't have an engine. It has to be towed off the runway. So we use a nose skid instead of a wheel because we have to go get it with a tow truck anyway. And that nose skid can act like a brake, helping slow the spaceship down as it comes back on the runway. The X-15 NASA aircraft, research aircraft, did the same thing. They used skids instead of landing. Great question. Next question is Izzy in San Francisco. How much does the spaceship weigh? The spaceship weighs about 30,000 pounds, including the ship, all the fuel and propellant needed to get the rocket motor to work, and the people on board. So it's pretty lightweight. Again, one of our design principles using air launch, let our spaceship be as light as possible. Helps it manage its energy a whole lot more. Next question, Nikki, 9 years old from Manchester over in England. Does the spaceship get cold in space? That's a great question. Yes, it does. It gets very cold in space. It can also get very hot in space if you stay there for a while. With no atmosphere to absorb the heat from the sun, the side facing the sun gets very hot, the side away from the sun gets very cold. Fortunately, our spaceship's designed to handle that, and it doesn't stay there all that long, so it's not a problem for us. Next question is Gabriela from Madrid. What's your favorite part of the spaceship design? All right, well, I'll tell you, I studied rocket propulsion back in college, so my favorite part is the big rocket motor in the back. Beth did a great job last week of telling you what the view from space was like and what zero gravity floating about the cabin was. But I'll tell you, for me, it's riding the rocket to get there in the first place. That's probably the best part of the spaceship in my view. Fantastic question, thanks. All right, thanks to everybody who submitted those questions in social media. We really appreciate it. Now let's go to the answers from Beth's questions that I asked you at the beginning. It looks like in the chat, quite a bit of you were listening and you got the answers right. Question 1, how fast did Beth travel on her way to space? The answer is about 3 times the speed of sound, more than 2,000 miles per hour. Question 2, what G-forces did Beth pull as her spaceship accelerated? That answer is about 3G, meaning she weighed 3 times more than she normally does while the rocket motor was firing. And the last question, how do astronauts wash their hands? Well, that's the fun one. They wash for 20 seconds, just like you're supposed to, but counting down while they do it, all the way until they get to 3, 2, 1, release, release, release. All right. Thank you all for joining our space chat today, and we hope to see you next week, same time, same place, where we'll be learning about how you actually build a spaceship. Go get started on designing your own video well. Safe and be well. Goodbye, everybody.
Wow. Yeah, wow. This is what works for those.
Look out there, man.
1 minute 15. You is incredible. Welcome to the club, astronaut.
Thanks, Space.
I like this club.